So yeah, once again, very happy to welcome Christian Gaetz from the Massachusetts Institute of Technology, who will be talking to us about separable elements and splittings of Weyl groups.
Okay, so thanks again for the introduction and the invitation. The work I'm going to be telling you about is based on two different papers. They're both joint with Yibo Gao, who's also a grad student at MIT. And I believe, yeah, he's here. So if you have clarifications or questions, feel free to ask those in the chat and he can help out with that. Or feel free to interrupt me as well, that's fine. Okay, I did want to say that the last time I gave this talk was in the University of Wisconsin combinatorial seminar, so I didn't actually have to update my title slide at all, which was nice. Okay, so here's a brief overview. I'm going to start by defining and talking a little bit about the combinatorics of separable permutations. So these are permutations which have previously been studied a fair amount over the last few decades. Then we're going to move to some new things, which is that we define separable elements in any Vowel group, so not necessarily a symmetric group. So it's going to take a while to go through the definitions and main properties of these. One interesting piece is that it's going to be characterized by pattern avoidance. So there's a notion of pattern avoidance of permutations, which characterize separable permutations. This will be a pattern avoidance in terms of root system, in terms of root systems, which was introduced by Billy and Postnikov, and our separable elements are characterized by this sort of avoidance. I'll also talk about some bijective and enumerative connections with faces of graph associahedra, which are certain polytopes. And then in the next section, I'll talk about splittings of Vowel groups. So for those who are in the pre-seminar, I defined what a splitting was, but I'll say what that means again. And I'll tell you about how separable elements give a solution to a problem of Björner and Wachs on how to characterize these splittings. We'll also, sort of for free as a result of some other structural properties of the symmetric group that we'll be studying, get a new combinatorial proof of an inequality due to Sidorenko about linear extensions and posets. Okay, so separable permutations. So a permutation is called separable if it avoids the patterns 3142 and 2413. So what do I mean by avoids a pattern? If you're not familiar, it just means that there's no subsequence of my permutation, if I write it in one line, which has the same relative order as 3142 or 2413. Okay, so I've drawn here the permutation matrices or diagrams for these two permutations. So you can see they're quite symmetric. In fact, they're inverses of each other. They are reverses of each other. They are complements of each other. Okay, so they're sort of mirrored permutations. There's another characterization of separable permutations other than this pattern avoidance one, which I think illustrates much better their structure. So that's in this lemma here. So a permutation W is separable if it can be decomposed recursively in a certain way. So if it can be decomposed recursively such that the permutation on the first M letters is separable itself, and the permutation on the second N letters is separable itself, and the permutation in the first M positions is on these smallest letters and the latter permutation on the largest letters, or vice versa. The first letters are the largest and the last letters are the smallest, and each of those is separable itself. So another way to think of this is that the permutation matrix of a separable permutation should be recursively constructed from smaller separable permutations by direct sum. So I take smaller permutations and I put them in blocks on the diagonal, or skew sum, where I take smaller separable permutations and put them on the anti-diagonal. Right, and it's not so hard to check that the permutations you get are exactly those which avoid these two patterns. And in particular, we can check that these two patterns do not compose in that way. There's no way for me to break up to break up this permutation matrix in such a way that it decomposes like a direct sum or skew sum. All right. So just a little bit of background in separable permutations. They were first introduced by these three authors in 1998. One of the reasons they've been studied is that testing for avoidance of a separable permutation pattern in another permutation can be done in polynomial time. It can be done much more efficiently due to this recursive structure, whereas the general problem is NP-complete. These appear in the theory of pop stack sorting. So this third bullet point is my favorite. I got it on Wikipedia. It has nothing to do with the rest of the talk, but I just was amazed that this was true. So suppose I have a collection of distinct real polynomials that all have equal values at some point. Okay, so I've got some polynomials, and they all intersect at some point. So because they're distinct polynomials, they have some order that they were in immediately prior to intersecting, and they have some order they were in immediately after the intersection point in terms of which polynomial is largest. The permutations you can get from this construction are exactly the separable ones. Fun fact. Okay. And
there's a question in the chat, sorry, from Sean Griffin asking whether this is supposed to be an if and only if statement. I think that's referring to the lemma on the previous slide.
The lemma is an if and only if, yes. That's a characterization of separable permutations. That's right, good question. Okay, and what we're going to be most interested in is some interesting combinatorics related to something called the weak order well, first the symmetric group and then later general Weyl groups. So let me talk about that. Okay, so the weak order or weak Bruhat order. So we'll start in just the setting of the symmetric group. So we'll take the symmetric group, which I'll write this fancy SN for, and we'll let SI just be the simple generator swapping I and I plus 1. So the right weak order is defined to have cover relations W is less than W times SI if the length of WSI is greater than the length of W. So if I'm going up. So that just defines the up direction. So here length is the minimal length of a expression for W as a product of simple generators. The left weak order is the same, except that I multiply by my generator on the left instead of on the right. So here they're both pictured for the symmetric group S3. So on the left is the left weak order, and on the right is the right. So these in general are going to be isomorphic to each other. The isomorphism from one to the other is taking the inverse of the permutation. But we are going to want to think of them separately because we'll be interested in statements that involve the left and right order at the same time on the same set of permutations. So we can see that cover relations in the left order correspond to swapping values which are adjacent, which are not necessarily next to each other in the word. So I'm allowed to swap 2 and 3 because the difference of 2 and 3 is 1, even though they're not next to each other. Whereas cover relations in the right order correspond to swapping numbers which are adjacent to each other in the permutation viewed as a word. Okay, so that's just the difference between right and left multiplication. So here's just a little bit of terminology for posets. So if P is a finite ranked poset, and I'll write Pi for the set of elements at the ith level of my poset. So it's rank symmetric if there are the same number of elements in the ith rank as in the ith rank from the bottom as in the ith rank from the top. It's rank-unimodal if the sizes of the ranks increase and then decrease. And I'll make this notation. So V sub x are all the elements which are greater than x in my poset. So that's a principal upper order ideal. The V is meant to be illustrative of the fact that I've got a unique element at the bottom, which is generating everything above it. And lambda x is similar. It's the principal lower order ideal generated by x. I'll also introduce this notation that if P is a poset, then P of Q will be the rank generating function of P. So it's just records for each element, Q to the rank of that element in my poset. All right. So here's a result by Fan Wei from 2012. She proved that if pi is a separable permutation, and I look in either left or right weak order, then this principal lower order ideal and this principal upper order ideal, they're both rank symmetric and unimodal, and the product of their rank generating functions is the same as the rank generating function of the whole weak order. So one of our results later on will be generalizing this result to all vowel groups, but we'll also have some results which are new even in the case of the symmetric group. So for example, all permutations of length 3 are separable because they automatically avoid these patterns of length 4. But we can see all intervals here are rank symmetric and rank unimodal. It's not very hard. In S4, if you draw out the weak order, you'll find that all of the intervals are rank symmetric except for 2, which correspond to our forbidden patterns 2, 4, 1, 3, and 3, 1, 4, 2. Those intervals will look like this, and those are not rank symmetric. Okay, so that's why those patterns are bad.
There's one more question from Alex asking to clarify how you define the generating functions for V and wedge.
Right, so that's just this general construction for posets. So I think of each of these as a poset in its own right with its minimal elements in rank 0. So even though X might be in rank I of the original poset, when I'm looking at the generating function for Vx, I'm looking at its own rank function with X in rank 0. And then I'm just applying this construction to that poset.
So in particular for wedge, the ranks go in the opposite order from the way they do in the typical?
No, not in. They'll agree with the typical one.
Oh, okay. So for V, they're shifted, but for wedge, they're the same as the full poset?
That's right.
Okay, thank you.
Okay. Let me move on. So let me do a brief crash course on root systems and vowel groups. So I covered this more extensively in the pre-seminar, and I think got mostly the same crowd here. So I'll go quickly. Here's one formula which I didn't give in the pre-seminar, which is an explicit formula for a reflection. So a root system is a collection of vectors contained in a Euclidean space that span the space, and such that here sigma A denotes the reflection across the hyperplane orthogonal to alpha. If I apply that to any other root or even to the same root, so this is an explicit formula for how you would calculate the reflection across the hyperplane orthogonal to alpha. But if you do that, you should land back inside the root system. And the vowel group is the group generated by these reflections for all the roots. Okay, so drawn here, this is the root system of type G2 that I referred to in the pre-seminar. Okay, so if I pick a generic hyperplane, that will partition the root system into a set of positive roots and a set of negative roots. And this determines the unique set, which I'll call delta, of simple roots, such that the simple roots are a basis for the vector space, and every positive root is a positive integer linear combination of the simple roots. So in this example, this dashed line is the generic hyperplane, which divides the set into positive roots over here and negative roots on the other side. My simple roots are alpha 1 and alpha 2, and you can check that all of these other positive roots are positive integer combinations of those two. Okay, a root system is called irreducible if I cannot partition it into two pieces such that all roots from one are orthogonal to all roots of the other. That is, if I had root systems living in different vector spaces and took the direct sum of those with the union of the root systems, that would be still a root system, but it would be reducible. Okay, so any root system is a union of a direct sum, if you prefer, of irreducible root systems, and these are the irreducible root systems. So A, N, B, C, D, and some exceptional ones. Okay.
So what do the arrows on the double lines mean?
So it turns out that whenever there's a multiple edge, the corresponding simple roots, so not the reflections, but the roots, will be of different lengths. So like in this case, I've got some roots which are shorter than others. And the, let's see, the greater than sign likes to eat the longer roots. So, or it points towards the shorter roots. So in order to construct the vowel group, which I'll talk about on the next slide, you don't need that information, but if you were to try to write down the actual root system, you would. And that's exemplified by these two families B and C, which differ only in that direction. So they'll have the same vowel group, but differently scaled root systems.
Thank you.
So the vowel group I was just referring to is the group which is generated by the simple reflections. So the reflections corresponding to the simple roots. So if W is any element of the vowel group, its Coxeter length is the smallest L, such that we have an expression of this form, writing W as a product of the simple generators. Such an expression is called a reduced expression or reduced word. So it's a fact that any finite vowel group contains a unique element which will denote W naught of largest length, a unique element of maximum length. And just as we did for the symmetric group, we can define the left and right weak order on any vowel group. So I'll write down exactly the same definition as I did. W is less than W times SI on the left if the length increases when I multiply, and similarly for the right weak order with multiplying on the right. Okay, so I know this is getting to be a lot of definitions and background. Hopefully it'll, well, at some point it will pay off. So the inversion set, if W is an element of W, its inversion set are those positive roots such that when I act by W, they get sent to negative roots. It turns out that the inversion set uniquely characterizes an element. So an element, if I give you an inversion set which is a valid inversion set, there's only one element with that inversion set. And we can actually characterize what subsets of the positive roots are the inversion set of some element. And that condition is called biconvexity. So S is called biconvex if whenever alpha and beta are both in the set and their sum is a root, then the sum must be in the set. And sort of dually, if alpha and beta are not in the set and their sum is a root, then the sum should not be in the set. Okay. It turns out that left weak order is exactly characterized by containment of inversion sets. So U is less than V in left order if and only if the inversion set of U is contained in that of V. All right, and the root poset is a partial order on the positive roots. So alpha is less than or equal to beta in the root order if beta minus alpha is a non-negative linear combination of simple roots. Any questions so far? All right. So let's do an example. So this is the root system of type an-1. So here, the vector space we'll work in, it's actually most convenient to choose it to be r to the n mod the all ones vector. So here the root system is the differences of the standard basis vectors. The positive roots are those ei minus ej's with I less than j, and the simple roots are those where I and j differ by 1. So it's not so hard to see that if I reflect across the hyperplane orthogonal to ei minus ej, that has the effect of swapping my ith and jth coordinates in my vector. So for that reason, the Vowel group is isomorphic to the symmetric group. So here's a picture of the root poset. So at the very bottom are all the simple roots, and I guess I've only labeled some of them here. There is a unique highest root, which is in general e1 minus en. All right. Okay, so here's something which might be maybe a bit less familiar to some people who are familiar with vowel groups. So if E prime is a subset of my ambient space E, then if I intersect E prime with my root system to form some set phi prime, that is itself a root system. So it's fairly easy to check that that satisfies all the rules to be a root system itself. And choosing the positive roots of phi prime to be just those positive roots which lie in the subspace is a valid choice of positive roots. So we'll always take that convention. If W is in the vowel group of phi, by the proposition on the previous page, its inversion set is biconvex. It's not hard to check that if I take a biconvex set and I intersect it with a subspace, that thing will still be biconvex. So because we had this if and only if characterization, that S was the inversion set if and only if it's biconvex, this new biconvex set, this intersection, must be the inversion set of some element of the vowel group of this smaller root system. So in that case, we'll call this smaller root, this element W prime, and we'll write that W restricted to phi prime, this subroot system, is this W prime. Okay, so this is some map from the vowel group of the large root system to the vowel group of the smaller root system. This is not a group homomorphism, but it's nice in some combinatorial ways. So for example, if W is this permutation in S7, and I take E prime to be the span of these two vectors, phi prime will be of type E2. It's just these vectors and as well as, so phi prime will be these two, and E2 minus E5 because that's in this subspace by adding those, and then the negatives of these. So that's a type A2 root system. In this case, the inversion set of W intersect this set is these two roots. So this is coming from essentially looking at this span tells me to look at only positions 2, 4, and 5 in my word. And I should look at their relative order. So here it's 3, 7, 2. If I sort of normalize those to the numbers 1, 2, and 3, take their relative order, that's 2, 3, 1. And that's W restricted to V prime. So in this case, we've sort of recovered the familiar notion of pattern avoidance and permutations, but we now have a definition which works for any root system. Okay, I'm finally ready to define for you what is a separable element in a general Vowel group. So we'll see later that in the case of the symmetric group, our definition coincides with separable permutations as we saw them at the beginning. So if an element W in a Vowel group of a root system is separable if either, well, we have a base case, so any element in the Vowel group of type A1 is separable. So the Vowel group of type A1 is just a symmetric group on 2 letters, and we say that both permutations of 2 are separable. If this root system is reducible, then we just require that all of the restrictions to the irreducible pieces themselves be separable. And sort of the non-trivial piece, the interesting piece is this third bullet point. So it says that if I'm in an irreducible root system, there should exist a pivot, which is a simple root, such that the restriction to the subroot system generated by the other simple roots is itself separable. So we've iterated down to a smaller rank root system. And when we do this iteration, one of 2 things must be true. Either every root in the root poset, which is bigger than my pivot, is an inversion of W, or none of these roots is an inversion. Okay? This is meant to model the 2 cases we had before with separable permutations, where I had direct sum and skew sum of smaller separable permutations. That's morally what's going on with these 2 possibilities here. Okay, so let's trace through an example. So what this is the root poset in type B4. This is a root poset of type B4, and let's say the elements in black are the inversions of some element, and the elements in white are non-inversions. And we want to know, is this element separable? So let's trace through the definition. Let me just check if I have a slide for this. Okay, so first, I'm in an irreducible root system, so I need to find a pivot. That is, I need to find an element such that a simple root such that everything above it is either an inversion or everything above it is a non-inversion. So we can choose alpha 3 because if I look at everything above it, everything in here is an inversion. So alpha 3 is a pivot. Now what I do is I iterate down to the root system where I remove alpha 3 and look at the root system generated by the remaining simple roots. So that root system is reducible. It's a disjoint union of these 2 pieces. Now I need to check that each of these is itself separable. So looking at this piece first, this is type A1, which is our base case. It's just a single node. So that's fine, that's separable. Now we look at this piece here. We again need to find a pivot. So now we need to find a simple root such that everything above it within this subsystem is either inversion or non-inversion. Now the pivot is alpha 1 because everything above it is a non-inversion. So we've succeeded in finding our pivot. So we iterate down again to what's left. What's left is just this piece. And now we're down to type A1, which is separable, so we're done. So this element was separable. Okay. So what do the collection of separable elements look like in, say, type B2? So I've drawn for you here the weak order for type B2, and the elements are labeled by their sets of inversions. So recall B2 has root system which looks like this. And I believe my conventions are that this is alpha 1 and this is alpha 2. So these are the 8 elements of the group. They are labeled by their inversion sets. and the circled ones are separable. They're all separable except for these two here. So why are these two not separable? For example, we can draw the root poset. So root poset looks like alpha 1, alpha 2, alpha 1 plus alpha 2, alpha 1 plus 2 alpha 2. And the inversion set, so let's take this one. The inversion set there is that alpha 2 and alpha 1 plus 2 alpha 2 are inversions, and the other two are not. So we can see here that there's no pivot. There's no simple root such that everything above it has the same color. So those two are not separable. All right. So pattern avoidance in the sense of root systems, this is using the restriction map of Billion-Postnikov from earlier. So an element W in the Vowel group, we say it avoids some W prime in the smaller Vowel group if there is no subspace such that when I restrict to the root system induced by that subspace, I get W prime. So here's our first theorem, which is an analog of the original definition of separable permutations as those which avoid two patterns. So we prove that an element is separable if and only if it avoids these two patterns in the Vowel group of type A3, which is the symmetric group S4, the two patterns of length 2 and B2, so these two bad things that I referred to there, and 6 patterns in type G2. Those are not so important because patterns of type G2 can only appear in other elements of type G2, so it's not so important. But in particular, this first bullet point means that the separable elements, as we've defined them, agree with the separable permutations because they're characterized by avoiding the same things. Permutations cannot contain these other kinds of patterns, so those aren't relevant for the classification in type A. All right. We also have an analog of the theorem that Fan Wei proved for separable permutations. So this is verbatim what her theorem said. So if W is an element of the Vowel group and it's separable, then the upper order ideal above W and the lower order ideal below it, they're both rank-symmetric and rank-unimodal, and the product of their rank-generating functions gives the rank-generating function of the full group. Okay. So this actually generalizes what might be a familiar statement and is hopefully familiar if you were in the pre-seminar. So it turns out that in a parabolic quotient, there is a unique longest element, and the parabolic quotient and that element is separable. And the parabolic quotient is the interval below this element in weak order. So this fact, in that case, ends up being equivalent to this fact, that the rank-generating function for a parabolic quotient times the rank-generating function for a parabolic subgroup is that of the whole group. You might know that in this case, there's actually an explicit bijection which realizes that, namely that if I multiply an element from the parabolic quotient times an element in the subgroup, I get a length additive bijection with all the elements of the Vowel group, and so I must in particular have this identity. That's suggestive that there might be something similar going on here, and in fact, we'll see that that's true. So first, I'm going to tell you about some combinatorial properties of separable elements. So if gamma is a simple graph, the graph associahedron is a polytope which can be defined as the Minkowski sum of the coordinate simplices corresponding to the connected subgraphs of gamma. I'm not going to go spend much time on polytopes, just the slide. So a collection of subsets of gamma is called a nested set if it satisfies some conditions, which I think I'm going to not go over carefully for now. And the poset of faces of this polytope is isomorphic, can be explicitly described by containment of these certain nested sets. What we prove is that these nested sets, which are in bijection with faces of the graph associahedron, are also in bijection with separable elements of the Vowel group. So in particular, separable elements are in bijection with faces of this polytope. And the map is simple. So this is some nested set, some collection of subsets of our Dinkin diagram. And you just take the product of the longest elements of the corresponding parabolic subgroups that will give you some element, and that's the corresponding separable element. And we also get an explicit rank generating function for the interval below a separable element, and it's written as this product of rank generating functions of parabolic subgroups, where n even means those sets which are at an even level of nesting inside this nested set. So, and I should mention that the rank generating functions of these are themselves known explicitly. There are products of Q analogs with exponents of the Vowel group. So this can be expanded as a quotient of products of Q integers. Okay. So yeah, let me do an example quickly. So if we're in S5, those are my simple roots. It's known that the rank generating function of the symmetric group is a Q factorial, where a Q integer is this sum. If this is my nested set, I take the product of the longest elements of the parabolic subgroups generated by these sets of roots. So for example, here I have all my simple roots, so I get the reverse permutation. Here I have only alpha 1 and alpha 2, so I just reverse this initial segment of length 3, and so on. I take all these products, and I get this separable permutation. And the rank generating function below the separable permutation is this, which is 5q factorial times 2q factorial over 3 times 2. And these are exactly the even and odd nesting subsets in this nested set. Okay, so now I'll get to talk about splittings. So given any subset U of a Vowel group W, the generalized quotient, so this is a generalization of parabolic quotients, are those elements such that the length of W times U equals the sum of the lengths of W and of U for any U in my chosen subset. Okay, so these generalized parabolic quotients, because if U is a parabolic subgroup, then this generalized quotient is exactly a parabolic quotient. Okay.
There's been a question in the chat.
Yeah.
Grant asks, do we know that all these parabolic longest words commute?
That's a good question. I tried to slip that by you. They don't commute. And so in particular, it matters which order you multiply these in. You want to pick an order which is compatible with the nesting of these subsets. So you want to multiply them in terms of a linear extension of the poset, which is these sets ordered by containment. And that's the right thing. Okay. So here's the proposition of Björner and Wachs, which says if we take, so this is the join. So weak order happens to be a lattice. So I can take least upper bounds and greatest lower bounds, least upper bounds being joins. If I take the joins of all the elements in U and call that U naught, then in fact, this generalized quotient is an interval in left order below this element. Okay, so generalized quotients are intervals in left order. So Björner and Wachs, in that same paper in '88, they made the definition of splitting. So a pair X and Y of arbitrary subgroups, sorry, not subgroups, arbitrary subsets of W, such that the multiplication map sending an X from X and a Y from Y to their product, if that is length additive, meaning that the length of XY equals length of X plus the length of Y, and bijective, that's called a splitting. So for example, as we went over carefully in the pre-seminar, the parabolic subgroup and parabolic quotient form a splitting for any subset of our simple generators. In the case where W is the symmetric group, Björner and Wachs asked for which right intervals. So they asked this specific case: if U is an interval in right weak order, when is this pair of the generalized quotient and the subset a splitting? In fact, we won't need this restriction that U be an interval in right order. We completely solve this case in the case of the symmetric group. So our theorem is that let W be any, well, first we prove the existence of some splittings. So if W is any finite vowel group and U is an interval in right weak order below a separable element, then this pair is a splitting. And what solves Björner and Wachs's problem is that in the case of the symmetric group, those are the only splittings. If X and Y are arbitrary subsets, which give me a length additive bijection to the whole group, then in fact, X is a left interval and Y is a right interval below a separable element of that form. We conjecture that this will be true in all Weyl groups, but so far we've proven it only for the symmetric group. So that solves Björner and Wachs's problem. Okay, so we see that this multiplication map is bijective if and only if U is separable. But what can be said about it in general? What can be said is this theorem, which we prove. It's simply stated, but it's surprisingly difficult to prove. This was the most difficult theorem in the paper, which is that this multiplication map is always surjective. So it's bijective exactly when U is separable, and it's always surjective. All right. So as an indication of the non-triviality of that surjectivity statement, I want to give an application of it to a problem about linear extensions. So a linear extension of a poset. So if I have a poset on elements P1 up to Pn, a linear extension just means an order preserving bijection to n, which is the set of numbers 1 up to n. And the number of linear extensions is denoted E of P. We are interested in two-dimensional posets. So these are partial orders. There are certain partial orders which are determined by a permutation. So Pi is less than or equal to Pj if and only if I is less than j and I appears before j in U when I write U as a word. Björner and Wachs observed that the linear extensions of this poset, the two-dimensional poset corresponding to U, they're exactly the elements of this interval in right weak order. That is, I can identify these linear extensions with permutations, and they are these permutations. The complement of a poset, of a two-dimensional poset, is a poset So for our purposes, let's just say that the complement of the poset PU is the poset PU times W naught, where W naught is the longest permutation. Now, if P is a two-dimensional poset, Sidorenko in 91 proved this identity, that the number of linear extensions of P times the number of linear extensions of its complement is at least n factorial. And there have been several proofs of this previously. So Sidorenko's original proof uses some recurrences and min-flow, max-cut sort of arguments. There is another proof which uses some special cases of the Mahler conjecture, which is a difficult conjecture in convex geometry, which is still open in general, but they use a special case. But none of the proofs to date have been very satisfying in that these are nice combinatorial objects that count linear extensions of some posets, and this is a nice combinatorial number, so it would be good to have an injection or a surjection which prove this inequality. And that's exactly what our surjectivity theorem provides. So recall that we proved this surjectivity claim by this result of Björner and Wachs. These number of linear extensions are sizes of weak order intervals. And if one flips things around and translates things correctly, then we get these two sets having exactly these sizes, and this being the symmetric group. So an instance of our surjectivity theorem is gives a combinatorial proof of this by showing that a multiplication map from a set of this size to one of this size surjects onto the symmetric group. So we get a combinatorial proof. And that answers a problem which had been stated by Morales, Pak, and Panova. And it also allows us to obtain a Q analog of Sidorenko's result. So yeah, I want to thank Alex Posnikov, Anders Björner, Vic Reiner, Richard Stanley, and Igor Pank for some helpful conversations, and to thank you for listening.
Okay, thank you. So applause doesn't work very well over Zoom, so there should be a button called reactions with a clapping reaction. Okay, and does anyone have any questions?
I have maybe a silly question.
Sure, far away.
I wonder what if there's a Weyl Group version of that polynomial crossing fact from earlier.
I thought for a few seconds about it, but didn't come up with anything. It's not clear what it would be, but no, I would really like it if there were.
Cool.
Sarah?
Ask a question. So I was wondering, to what extent can you do this for infinite Weyl groups too? Can you restrict yourself to a particularly nice interval in an infinite Weyl group? So one thing that Lakshmi Bai was using for a while was, for example, like in the affine SN case, she was using the element S1 times S2 times S3 up through Sn, and then repeat again S1 times X2 times. You get a particularly nice top element. And so if you do that enough times, you will of course get any reduced word in there. So it has sort of a lot of things below it. Could you consider looking for separable elements that extend to infinite Weyl groups somehow like that?
Right. So we thought a little bit about this, not a huge amount. So certainly the questions about, say, splittings make perfect sense. And you can ask, what are all the splittings of this infinite Weyl group? We don't quite know how to define separable elements in these types because, okay, so first of all, the root system is not, so there's some notion of root system, but it's not finite. And so it's not possible to have these two different kinds of pivots where you have a full pivot where everything above it is an inversion, because that will be infinitely many things, and there's nothing of infinite length. That's related to the fact that we have no element W naught. So not having a longest element sort of doesn't give us these two different kinds of pivots where you have a direct sum and a skew sum. And because of that, it's sort of hard to get off the ground with this recursive definition, and so there needs to be something else, which we're not sure what that is.
Well, there's something else that's obvious, I guess, is you take this list of patterns that you have and you say, well, what are all the elements that avoid those? And I was thinking about using the root system, the extension of the root subsystem pattern avoidance that Tom Braden and I had in a follow-up paper to the one with Alex Posnikov.
Okay, yeah, we haven't thought about doing that for infinite
root system that goes with that. So the pattern avoidance business can be extended to any Coxeter group that way.
Yeah, we haven't thought about that. I would guess that if you want nice properties, there are going to be more things you should forbid, because so for example, so I phrased this all in terms of Vowel groups, but if we went to finite Coxeter groups, so I add in the dihedrals, then essentially for each dihedral you have to throw in a bunch more patterns. And so when you get higher and higher labeled edges, I think you're going to get more patterns that you have to throw out. And so I'm not very confident that these are the right ones to forbid in general, if you went to infinite. But yeah, it's definitely, some of the applications and splittings and so on make good sense. And so it would be good to understand what's going on in infinite Coxeter groups, but we're not sure.
I'm particularly impressed with this combinatorial proof of the product formula there, the linear extension product greater than or equal to n factorial. That's neat.
Yeah, that was nice when we realized that.
I have another question if that's okay. Oh, go ahead.
I guess my question was also about that surjection. Do you know? So you have this conjecture about the equality for separable elements holding exactly in the other Weyl groups exactly in the same conditions as the symmetric group. Do you know if that surjectivity argument also works?
So we conjecture surjectivity is true in other types, but haven't been able to prove that. Yeah, it's sort of surprisingly annoying. And I know Igor Pak and other people had looked at this as a way to get a proof of Sidorenko's identity, and agreed that it wasn't easy. So it seems to be some, I think, lack of general understanding as to why that should be true. But our proof doesn't extend to other types, but we conjecture that it is true.
I had a question, if that's okay. So for your definition for separable, you're really using the root system or the root poset, in order to define it. Do you
Sure.
have a way to define it without using the root poset at all, or?
Well, the pattern avoidance characterization doesn't rely on the root poset. So
do you know? Oh, sorry, keep going.
I guess it relies on a choice of positive roots, probably, but it doesn't. It's not phrased in terms of the root poset.
So the reason I'm asking, Michael Kuntz and Christian Stumpf have a way to look at root systems in the non-crystallographic cases, so in the other Coxeter types. So I was wondering if this pattern avoidance and the root poset that they kind of generated for these might have, you might look at that angle to see if this is workable in all Coxeter types, or?
Right. So we have considered looking at the other finite Coxeter groups, and essentially we are able to say what everything means and what the theorem should be and so on. The reason we didn't bother to work in that generality is that first, finite Coxeter groups is not very much more general than finite Vowel groups. All I get is the dihedrals, and the two exceptional groups, H3 and H4. And the dihedrals are simple enough that sort of all the theorems one would prove are obvious anyways. And it turns out also that in the dihedrals, there's not really very many separable elements. It's just the 3 elements at the bottom and the 3 elements at the top. And so we didn't feel like going through extra trouble to just get H3 and H4, which are just 2 exceptional cases, which you can check explicitly. But I think everything would work if you went through the care to define things properly.
Thank you.
I have one more question, if that's okay. I'm a GLNFQ fanboy, so have you thought about separability and splittings and things for GLNFQ? With like absolute order or something?
Right, so absolute length feels very different. I guess there's not really a good analog of Coxeter length for GLNFQ.
Mm-hmm.
I mean, I think the question still makes sense. I just doubt anything to do with absolute length would be related to sort of our story, but like there are interesting things going on.
Cool, thanks.
Okay, well, if there are no more questions, let's thank Christian again.
Thanks.
Wow. It's a really nice talk. Thanks, Christian.
Nice work.
My pleasure.
And so if you enjoyed this talk, there'll be another one at the same time again next week. Time to see you all again.